And I'll do a quick introduction to you if you don't mind.
Sure.
Yeah. So today it's our great pleasure to welcome Dr. Benji Maruyama to share his research and insights with us. And Benji is a principal material research engineer at the United States Air Force Research Laboratory, and he's a true pioneer in accelerating material discovery. If I recall correctly, as early as 2016, Benji and his team led a groundbreaking effort in our fields and published the first demonstration of their autonomous research system, the ARIS. And it is a fundamental milestone that laid the groundwork for the entire domain. And also it shifted the way we think about automated or even like autonomous material exploration we are doing. And Benji, we are excited to hear about your amazing work. And now the floor is yours, please.
Thanks, Renzi. Appreciate the introductions. Very nice of you. Happy to talk to everyone and looking forward to interactions. And so, as Renzi said, I'm at the Air Force Research Lab, and I'm the lead for autonomous materials research there. And let me see, make sure my slides are advancing. There we go. Okay. So if you're not familiar, the Air Force Research Lab, AFRL, is essentially corporate R&D for the Department of the Air Force. And so we have a very broad mission. So leading discovery and development of integration of affordable warfighting technologies for airspace and cyber. And so you can see that not only do we do air, right, so airplanes, but actually the Space Force, and we have as well the cyber mission. So, and when we think about that, we do from basic research, like in academia, all the way through development, tech transition, sustainment, so the whole range of materials development and deployment. And so if we think back just a little bit more on AFRL, we have locations across the US, and we actually have locations abroad. But going back, of course, to the Wright brothers in 1917 is actually when AFRL, the progenitors of AFRL were started. Of course, you know, we have significant contributions in all fields, not just materials, but electronics, GPS, all that kind of good stuff. We're about 12,500 people. We execute all of AFRL, about $7 billion, and work with, as I was saying, customers not just in academia, but also industry, as well as international partners. So that's a bit about who we are. And of course, I'm at Wright-Patterson Air Force Base, which is in Ohio, which is only about an 8-hour drive from U of Toronto. So I've been out a number of times and had great interactions. Okay, so let's talk about what's wrong with research. And so we know that research is getting slower. It's less impactful. We're putting more money in. And by this MIT study, you know, there's less out for that money. And, you know, part of it is just to think here a little bit is, you know, there's less risk taking in research. If you're a young, you know, professor or graduate student, you might not want to take too big of a risk, right? You might have to, it might be great to get the super, you know, Nature paper, but if you don't, what happens? And so people are let's say more conservative. But of course today, the answer that we'll talk about to make research go faster is really about AE, autonomous experimentation, which makes research faster, better, and cheaper. And so thinking about revolutions, right, we have previous revolutions, the industrial revolutions, where machines, steam-powered engines, right, took the place or leveraged human manual labor so that, for example, one farmer with a tractor could now do the work of 100 farmers. So that's manual labor. And of course, it doesn't have to be the strength, but just the repetitive motion. So if we think as researchers and especially students, if you're constantly taking a sample and moving it around or polishing or pipetting, all of those are manual actions that are, you know, laborious, right? It's toil. And so I guess we think back to the word laboratory, right? The word labor is in laboratory, and that's kind of what we do. The other part is in cognitive revolution. So if we think about compute, human computers, the image on the left is of human computers back in the old days before uh, uh, electronic computers. When you said computers, you were talking about people, human computers, mainly women who were doing things like calculating trajectories for Apollo spaceships. And then, the middle image is where the beginning of mainframe computers, where they're tracking satellites. And now, of course, where we are today is compute is almost transparent to us. It's embedded in our phones and what we do with tremendous compute power. So the idea is, how can we get to robots, autonomous robots that can perform both manual and cognitive labor? And so that's our research revolution. So that's where we are here, where today, if we walk into most laboratories, my contention is that if Madame Curie, right, time traveled to our current day and looked at our workflows, right, here she is with a flask, and here's a researcher pipetting manually into test tubes, that the workflow of us researchers would be familiar to her. But of course, now we're building this autonomous research revolution where autonomous robots can perform both the manual and cognitive labor, and in so doing, speed progress by orders of magnitude. So what is autonomous experimentation? Here's our additive manufacturing Aries, AM Aries, squirting out a little bit of caulk and trying to optimize printing a square, a filled-in square. And so you can see that the robot prints out the square, it takes a picture of it, does some image analysis, and then scores how well it's filled in that square. And then based on that and a decision process, in this case using Bayesian optimization, it adjusts the different printing parameters, and over tens of experiments, it's now taught itself how to print this very simple square. So that was a demonstration for additive manufacturing with closed loop autonomous experimentation. The original system that Rinzin mentioned is our original Aries, which we published in 2016. I was just talking with Dalen Hooper, a co-inventor of Aries, and so our first fully autonomous experiments happened in around this time in 2014. We were able to go fully autonomous closed loop. And so what happens in Aries is essentially each of these pillars, these micro pillars here, is an experiment. And so for carbon nanotube synthesis, which is what we were working on, you need a source of heat, which was in this case a high power laser hitting this pillar and heating it up. Catalyst, which is these little dots on the pillars. So this is an iron nickel transition metal catalyst. And then a source of carbon, which was ethylene for us for the most part. So you can imagine the ethylene gas flowing into the reaction chamber. So that combination of the ethylene carbon source, the catalyst, and the heat enabled us to grow carbon nanotubes. And we knew that because we were able to take the scattered light from the micropillar and send it over to a Raman spectrometer. And so if we think about self-driving labs like self-driving cars, the Raman spectrometer was our eyes, right? The cameras that told us where we were going. And so so we could do the experiment, collect the Raman spectra as a function of time, watch the nanotube grow up, see the growth rate of the carbon nanotube. So you can see here, as the Raman G band grew up as a function of time, you could see that the growth rate had a certain peak and then fell off over time. And so this flow of plan an experiment, which in this case was a random forest planner, we said, okay, what do we want to do? What temperature do we set up? What gas composition? What pressure? Then we do the experiment, collect the data, and then analyze the data to see what the growth rate was. And then based on that growth rate, the results that we got, plus our objective, right, what we wanted to get to in this case, which was to accurately predict the growth rate of the carbon nanotubes, we would then plan a new experiment. So what is the next best experiment that we can do to achieve our goals of controlled growth rates? And you can see on this panel over here, this is growth rate versus the experiment number. In the early experiments, these are hundreds of experiments. Each of the dots is an experiment. You can see that despite the fact that that solid line is what we thought the growth rate would be, there's a lot of scatter. This is on a log scale. Until about experiment 500, when all of a sudden Aries locked in. So there's very little scatter from here out. And you can see that Aries essentially had taught itself to grow carbon nanotubes at controlled rates. So ours was the first demonstration of closed loop autonomous research for materials, and we published that in 2016. So if we sort of abstract this autonomous experimentation process, we have this flow block here. So plan the experiment, execute the experiment, analyze it, and now go back and replan. And so, the characteristics in the plan can be, to predict. There's this idea of explore versus exploit. Sometimes, if something is getting better as you go up in temperature, it keeps going better. Well, sure, keep going up in temperature until it stops getting better, right? That's the exploit part of things. The explore part of things is, okay, well, I've done that and it's not getting better anymore. Maybe it's time to go try someplace else where I don't know what's going on. I have a lot of uncertainty, and that's exploration, and maybe I'll find something better. But ultimately, you have to decide what to do next. And so then you go and do that experiment, and that experiment in the abstract, for us, it was synthesis. You make something, but it could be a characterization, and that was actually Jay's early work at NIST, doing X-ray diffraction, or it can be the result of a simulation. So you do a simulation and you see how it turns out. And then in the analysis block, you want to extract that information. So you interpret, understand, right, the growth rate. You might look at it in terms of some expected behavior. You might try and reason and understand over it. So that's the kinds of things that can happen in this block over. And of course, ultimately, the key part of autonomous experimentation is iteration, that you try something, you see what happens, and based on those results, you go back and try something different, and you iterate many, many times. Could be tens, hundreds, thousands of iterations. But the idea, and this is important to distinguish autonomous experimentation from, say, the previous high throughput or combinatorial approaches, is that more iterations beats more experiments. And I would say the other part to the power of closed loop is that we can just say, okay, I want the best growth rate, right? Optimize the growth rate, or, if it's solar cells, optimize the quantum efficiency, whatever it is. But the objective of the campaign of experiments could also be to test a hypothesis. So if it's the ideal gas law, you might say, I hypothesize that the ideal gas law is true. Then the campaign decision process is, what experiment can I do next to best confirm or negate that hypothesis? And so that's important there. And it might not be the way we were normally taught as researchers, where you hold everything constant and you march along temperature or pressure and you to build up a response function, and that's the campaign. It might be something like if you played the game, the kids' game Battleship. In Battleship, you have pegs and you try and guess where your opponents put their ships. And what you typically don't do is march along A1, A2, A3 the way we were taught to do. You sort of explore until you find someone's ship. And then once you find one, you try and finish off the ship by exploiting right around that. On the left block here, we have the human side of things. So initialize, we have to define the objective of the experimental campaign, specify constraints, and provide prior knowledge. And of course, at the conclusion, right, you might have achieved your objective, you report, you update your repository. But the distinction again between automation and autonomy is automation is pre-planned experiments where there's no autonomy to deviate from those pre-planned experiments. Whereas in an autonomous system, right, the system has the autonomy, the authority to design its own experiments, in our case, using artificial intelligence and machine learning techniques. There are certainly others who have done autonomous experimentation. I won't go through in detail, but I'm sure you'll be able to find these. So Keith Brown has his Bayesian experimental automation autonomous researcher. But Keith did some great work in actually quantifying the speed up. So he found a 30x improvement than a grid-based search, and actually a 300x improvement over normal search when he was using physics-informed models. So a great benchmark. And then Milad Al-Bassani at NCSU has his artificial chemistry. So in a different sort of domain, he's using flow chemistry and doing great work in that area. Of course, self-driving labs, the work of Alan, Jason Hine, Curtis Berling-Witt in Canada is doing very good work in self-driving labs for, among other things, looking at laser organic dye materials. And Jay, I don't know if hopefully Jay's on, but anyhow, doing very nice work in comparing, right, different decision algorithms. So we did a paper. This is Jay and I and the people you see pictured there. If you're interested in hearing more, reading more, highly recommend you go to this paper. Despite the fact that it's 4 years ago now, I think it's held up very well as far as seeing where the community directions are going, and by and large, the community has gone in these directions. So just to talk about some recent development, the Materials Genome Initiative, the MGI, issued some challenges. So I'll show you the work up to that. So in June, we ran a workshop, and in July, we reported out the results of the workshop in the Accelerated Materials Experimentation enabled by the Autonomous Materials Innovation Infrastructure, the AMII. And so, I, along with my colleagues, Cosima Boswell-Kohler, Jim Warren, Charles Yang, and Lisa Friedersdorf, were very happy to do this workshop and report it out to the MGI. And, you know, this idea was to inventory the national AMII and identify opportunities for potential challenges, as well as gaps that we need to fulfill those goals and targets. And so our findings are online. The report is in the QR code, but there's a need for significant infrastructure improvement, workforce development. So we need to get the right people trained to do autonomous experimentation. We have issues with hardware, decision methods, integration of modeling and simulation, software, standards and data structures, and better ways to share and give access, so fair data standards. Safety and security is important, as well as shared facilities, and thinking about digital twin for both research as well as scale up. And then there's a need for consortia of public-private partnerships. There's in the report, if you go to it, you'll see a landscape of as reported by the participants. And you can see just in general, discovery and design outward is more mature, more hits. Synthesis is pretty good, characterization is okay. But by the time you get to things like scale up and manufacturing, qualification, certification, recycling, end of use, there are very few examples amongst the different materials classes. And so you can see, you know, where the gaps are and where we need to go forward. So very exciting. What was it now? It was almost 2 years ago, I guess, last year. We were able to run a round table. This was hosted by Donna Weinstein, who was then at the White House Office of Science and Technology Policy in the US. And with her, we talked about autonomous experimentation for semiconductor materials innovation. And largely this was about how do we eliminate PFAS, these forever chemicals, from semiconductor microelectronics processing. So very exciting work there. And that led to AI aspirations. So out of White House OSTP, there were 7 different AI aspirations. So good things that AI could do for the nation and for the globe. And one of those 7 things, and these ranged from, better government services to better human health to better educational opportunities. And there was one for materials, which came out of the roundtable, and so it's semiconductor materials innovation for autonomous experimentation. And so that was very exciting as well. Out of that came funding. So there was $100 million allocated and announced by the Secretary of Commerce at that meeting for sustainable microelectronics. And so that project was out there. I don't know where it stands right now, but hopefully we'll have some announcements on winners for the Charisma program. So very exciting. And then finally, the MGI issued the 2024 MGI challenges. And you can see the 5 challenges there. So, and they sort of align with or led by different agencies within the federal government in the US. So point of care tissue mimetic materials for biomedical devices and implants. So think prosthetics. Agile manufacturing of affordable multifunctional composites. That's mainly led by the Department of Defense, as is the quantum precision navigation timing. And then DOE Energy's focus challenge was on high performance, low carbon cementitious materials. And then of course, the sustainable microelectronics that we already talked about. There's also a great MARTA meeting in this area as well. Okay, so from high level to low level, what I work on again is carbon nanotubes. I really believe that carbon nanotubes can save the world. And so, if you hadn't heard of carbon nanotubes, they've been around for a couple of decades, and they have a tremendous range of applications from fibers for structural applications, filtration membranes, electronics that are way better than silicon, thermal materials, energy storage. So great applications. Why don't we see them? Well, the truth is that there are significant nanotube applications in batteries. Lithium-ion batteries, for the most part, contain carbon nanotubes. But realistically, they have not delivered on their promise, and that's mainly because we can't not make them at scale and at cost. So I was very inspired by the Rice Shell ARPA-E program, where we would take methane, which is currently just burned to generate electric power or heat. And it's interesting, right? Because the energy, the caloric value is mainly in the hydrogen. And so if you pyrolyze that methane, CH4, you send the hydrogen to the hydrogen economy. Now it's clean energy, does not generate carbon dioxide, and take the carbon from the methane and convert it to carbon nanotubes. That way the carbon is now sequestered, so no CO2, no global warming. And if you do this at scale, you can get a 20 to 40% reduction in global CO2 emissions. That is the save the world proposition. The big asterisk there is that you have to do this at a scale of hundreds of millions of tons per year. And we have not figured that out. And the only way to get that, if we just do it the normal way where it takes decades, it won't work. We won't meet the 2050 goals. And so the way to do it is by using autonomous experimentation and self-driving labs to accelerate science. And so just to think about then what we have done recently in understanding carbon nanotube synthesis, I'll give you a background. So here's our iron catalyst for carbon nanotube growth on a support, and you can see that if you add carbon in the right way with heat, you grow a carbon nanotube. The thing is that, mostly we think about it, one catalyst gives you one nanotube, not normal catalysis. More catalyst gives you more nanotubes, but also the diameter of the catalyst controls the diameter of the nanotube. So that comes into play a little later. When the way you normally put down your catalyst is to deposit a thin film of iron that is oxidized when you expose it to air. And then you heat it up and reduce that iron to these little catalyst particles. And these small is like 1 nanometer across. So that process involves reduction, de-wetting to form the particles, and then growth of the carbon nanotubes. But as soon as you reduce, all of these tiny little particles start to Oswald ripen. So essentially that's a phenomenon where lots of little catalysts become fewer bigger catalysts, and that's not good for carbon nanotube growth or yield. So the other background, thinking about that reduction step where we go from the oxidized catalyst film to the reduced catalyst nanoparticles, is taught to us by the Ellingham diagram. So this is good old-fashioned metallurgy. It's undergrad metallurgy that tells you as a function of temperature and the ratios of different oxidizing and reducing gases, when will an iron, so if you think of it in this direction, when will iron oxide reduce to iron? And so using this Ellingham diagram and going back to, of course, the thermodynamics, you can tell when the iron oxide is expected to reduce to iron metal, at which point it's an active catalyst. And so that's given by this thermodynamics equation where delta G equals RT log of the activities of the reductants over the oxidants. So in our case, we worked with Professor Chi-Woo Park, who's now at University of Washington, to use a jump regression planner. And I can go into the details if anyone's interested, but essentially it replaces a normal Gaussian planner with something that expects a discontinuous jump, which is appropriate for this phase transformation between oxidized iron and reduced iron. And so with his planner, we were able to do experiments in what we're calling thermodynamic space, but this is that log of the partial pressures of the reductants over the oxidants versus temperature. So that's essentially this equation here. And you can imagine, right, this is a log scale, hundreds of degrees C. It's a huge parameter space, and Chi-Woo's jump regression algorithm told us where to search to find that thermodynamic boundary where the oxide of iron was in equilibrium with its reduced metal. And so this dashed red line is a line of constant delta G, where that, again, the oxide is in equilibrium with its reduced metal. And so if we look at it, the experimental results, each of these diamonds and circles is an experiment, and the bigger and darker the marker, the better the yield. And so you can see that pretty much for two different film thicknesses, the optimal growth happens along a line of constant delta G. And that's in terms of the ethylene partial pressure, the CO2 partial pressure, and the water partial pressure. So essentially our hypothesis is confirmed that the highest activity is where the oxide, the catalyst is reduced metal is in equilibrium with its oxide, because that's when it just starts to grow and it doesn't Oswald ripen very quickly. So it's optimal as far as the catalyst number density and activity. If we were to look along this line of constant delta G, essentially collapse it so that we're just plotting the delta G as a function of yield, you can see that there is a very sharp transition, this jump that we talked about for Chi-Woo's effort, where essentially it is as we predicted, growth is and yield is optimal as at a constant delta G. So here we have more oxidized system, here we have a more reducing system, and you can see that the yield jumps up for both the 1 nanometer thick film and the 0.3 nanometer thick film. And I would say this is a great result for carbon nanotubes because what we looked at is 4 different parameters. We collapsed 4 parameters, right? Temperature, 3 different gases, and 10 orders of magnitude of partial pressure ratios and 500 degrees C all into one plot. So I was super excited about this result. And then now we're trying to broaden the model, the hypothesis, to say, okay, we did this for iron, but it should be generalizable, right? It should be true for all catalysts. And so we then went and did cobalt, and cobalt is right where we expected it to be. So check, we now have 2 metals that behave the way we expect. And so, the implications for a nanotube are great, right? So it says not just people in the nanotube community, they find a growth recipe and they say, this is the optimal growth recipe. Well, that's the optimal growth recipe for that temperature or for that catalyst. But now we have a vehicle, right? Essentially an understanding where we can say, we can tell you how to make a bad catalyst into a good one by controlling the thermodynamics. So it's a great tool. I won't go into this for time, but really this is about how we find that balance between Ostwald ripening and catalyst activity. Okay, now I'm going to go back out and think broadly about the future of science. So what can AI do for science? There's a Nobel Turing Initiative led by Professor Hiroaki Kitano in Japan. This challenge which says, can we build machines that can win a Nobel Prize by the year 2050? And so this is this idea that AI can do science, as we can AI scientists. Now, I would disagree. I think that we don't want to have AI scientists that replace humans. I think we need AI scientists that team with human scientists to do better. But the important points for Kitano is that autonomy is not the same thing as intelligence, right? You can have the best AI model out there and find great solutions, but if you do not have the autonomy to act and to confirm those beliefs, then you can't advance science, right? You have to demonstrate what you're doing. That's a scientific method. On the other hand, you can have autonomy without intelligence. So if we think about a mousetrap, if you set a mousetrap and walk away, you have delegated decision authority to that mousetrap. That mousetrap has no intelligence. So a lot of times we confuse the two, but the Nobel Turing Challenge, according to Kitano, and I agree, will be won by AI scientists that have both intelligence and autonomy. So both the ability to think through complex problems and the authority to act on those rationale to do experiments and prove or confirm different hypotheses. And then we need a public-private partnership. So I think University of Toronto is very far along, especially in the acceleration consortium. We'd like to do some of those things in the US and have that partnership between government and industry and academia to attack all these kinds of problems that we're looking at. So I'm going to skip this one and just because we're a little short of time and go on to citizen science. So we talked about this in the paper, but and done a lot on this. As we make experiments cheaper and more productive, they become more accessible to citizen scientists. So those of us who aren't in graduate school or in a big laboratory. And that means that more people get to do research. And that's a good thing because now I think very few of us have run out of ideas. Mostly it's just that we don't have enough time or enough robots to do the research for us. And as we make research more accessible, we'll have more people doing research, which I think is a good thing for society. Less bias on who gets to do research, and we get to do non-traditional people doing science. So not just those of us who who managed to get into great places like the University of Toronto. And of course, the other thing is, and I talked about this earlier, is that if you can do, 1,000 experimental iterations and it only takes you a week, you can, how many of us have wasted a week doing experiments that didn't work out, right? If you can do that, you can now try very risky things that have a low chance of success, but you know what? It's only a week. So I can try things that I would not normally try that have potential for very high payoff. So it changes the risk reward balance for doing research. Safety and security, though, is a very important thing. We need to make sure that people are not accidentally harming themselves or others. And of course, security, we have to avoid intentionally harming other people's or giving people the access to do that. So we have to find ways of red teaming, making sure that we're thinking about how things can go wrong and implementing guardrails and community standards. And again, just to think about autonomy, this is a definition that we can use. So autonomy is delegated decision authority, where the delegator, the delegating authority, retains the responsibility for the actions and consequences of the agent to whom it's been delegated. And it's bounded, it's not, you can go off and do anything. It's not carte blanche. You have to do things within the scope that's established, and it's revocable, right? And so we want to make sure that it's not just robots that go off and, do bad things Terminator style. We want to make sure that autonomy is revocable. And again, back to science and society, right? Scientific, this is in the obituary of Everett Mendelsohn. Scientific revolutions require more fully developed citizen participation. So that's the citizen science, something which is hard because knowledge level might be high, but how do you bridge that gap? And I think, nowadays with the internet and maker spaces, there's actually a vibrant citizen science population, but they don't have the tools, the FTIRs, the robots. And so if we can make these robots low cost, we get to this thing where we say science, I guess we could say in some ways, is certainly too important in our lives to be left to experts alone. We're the experts, right? So if we have more than just us doing science, it gets better as a whole. So to that end, we've built Ares OS. That's our open source autonomous research software. The Git address is down below there. We're at version 2.0. And you can think of it as the core operating system for doing autonomous experimentation. And it's generic. It's now been applied to not just nanotube synthesis, but chemistry and 3D printing. So we believe it's generic. And we want to reduce the barrier to entry for anyone to do autonomous experimentation. And so as a demonstration, we have a low-cost autonomous 3D printer. This is with Greg Ganatano at Bert Peterson at AFIT, which is the Air Force Institute of Technology. And so what Greg did was supply his autonomous 3D printer, and this is really just an Ender 3D printer, with a camera and a Raspberry Pi board. And with that, he gave the printer 3 different unknown filaments, and through a dozen or so iterations the printer taught itself how to print these bunnies to better than the manufacturer's specifications. And more recently, we've been able to do that, so better than manufacturer's specifications, and do it 50% faster than the fastest speed. So that was a great result on its own, but what's great about for citizen science is that that system is only $300. So at $300, we can now get this into colleges and universities and maybe high schools and libraries and maker spaces so that everybody can try out their own algorithms for how to best optimize print. Or they can make modifications to the printer because it's open source and do things better. So it's a platform really for teaching artificial intelligence, and autonomous experimentation. And we actually recently have, there's an agreement between the University of Buffalo and DCS to essentially do a demonstration for the University of Buffalo so that their graduate students can use this as a teaching tool. So with that, I'd like to acknowledge support from NRC, which is in the US, the National Research Council in the US, as well as the Air Force Office of Scientific Research for financial support, and then our collaborators across AFRL at Penn, Buffalo, OSU, Florida State, UIUC, and Brookhaven National Lab. And finally, I'd like to thank you for your attention and for the invitation to present to you. Be happy to answer any questions.
Thank you so much, Benji. Yeah, thank you for this amazing talk, and like the perspective and insights you shared with us are really valuable. So I think we have time for maybe three questions. So if you have any, feel free to unmute yourself. Yeah, please unmute yourself, Daniel.
Hi, Benji. Great talk.
Thank you.
It's really cool to see sort of like the cutting edge of self-driving labs that are up and running. I'm super interested in the previous slide 49. This idea of sort of
Yep.
like open source SDLs. First, how is dissimilarity score? How is it characterized? Is it just using the camera?
Yes.
Very
Just
nice.
a camera and controlled lighting. The lighting is important, and it's kind of finicky, but yes, it's just a camera and a lighting system.
So is this? I haven't looked into the paper, and I will do so. Is there some sort of database, cloud-based database where these results get stored to? So, for example, if you had 2 or 3 of these platforms in different places that they can sort of work off one another and share information, and
Yeah,
then reproducibility then becomes an issue. I'm just wondering if you have any thoughts on that, or if that's been considered.
yeah, super point. So my grand scheme for this kind of printer is I'd like to use it as a challenge. So the Hiroaki Kitano, the guy I talked about earlier, he developed a RoboCup challenge for autonomous robotics, and that actually defined the field for collaborative autonomous robotics for the past couple of decades. And so what we'd like to do is put together a challenge for AI, AE self-driving labs, and could use this as a platform. So so everybody works off of the same sort of robot and shares their results and compares or maybe competes. And so you could imagine a competition where everybody starts with the same hardware and you have a new shape, right? Something that's challenging. And whoever has the best algorithm to get to that shape wins the prize, right? And so I think it's a really powerful way of getting lots of people involved who might not otherwise have access to do that.
I love that idea. I'm super interested in stuff like that. Thank you. I appreciate it.
Thanks. Yeah, it's crazy because I during COVID I was supposed to go up and spend time at Toronto with Jay, and this is the thing we wanted to work on. So if anyone out there is wanting to work on it together, let me know because I'm happy to work on it. Continue to do that. There's a lot to do.
Awesome. I'll reach out. Thank you very much.
Yeah, feel free to unmute yourself, Bill. Yeah, I see your hand is up.
If you don't mind, I have a different perspective on the idea of citizen scientists and democratization of science.
Please.
I feel like the problem with science is like there's too much bureaucratic process of verifying your science is true. It's not really that just a lack of equipment of doing actual science, right? Like with the current scientific model, it's like everything is false until you can prove it's true. And the process of proving it's true is not just showing it's true, but it's to convince the scientific community that it is true. And the problem is like too much like process of gatekeeping science by the scientific community. It's like you have to like do so much peer review, so much literature review, and you have to like defend yourself, get picked apart by like from any perspective on that. And until then, you are not your science is not true, and you will not be accepted. I feel like it's not really the problem of lacking the ability to do science. It's more like lacking the ability to like verify and process science,
So
and it's not really.
yeah, I mean, you make a good point, that there is a lot of gatekeeping. I think both things can be true. But you know, to that end, I think, at the core, right, of sort of the age of reason, scientific revolution is that, if you make an assertion, you have to support it and you have to confirm it experimentally. And I think, you know, it's true that, that peer review is gatekeeping, and I think it's done a lot to up the quality, but you're right, it does hold things back. And so I would say, you know, in the process of getting to citizen science, where, you know, probably people can't take the time to do all of the, you know, peer review. Maybe there are certain thresholds where we can have, you know, something that's more dynamic. And to that, you know, I think the maker spaces, the maker community has done a lot towards, you know, you put something out there, say, hey, I did this way. And, you know, people like it or they don't. They try and do it themselves and they give feedback on it, right? And so it's much more informal, and hopefully it addresses some of what you're talking about. But I agree with your point.
Oh, great. Thank you, Benji. So is there any more questions? We can have more ones. If not, I'll use my privilege to ask a question. So yeah, I've been thinking about the future of the future in our field for a while, and great um like the scientific AI thing you mentioned, and totally like answer that. So my question actually is, so it towards to realize to have a AI scientist, with the prioritize, with the how to say, like with the top one question or challenges we need to solve toward that. So I know like we are working on some infrastructure, we are extending different self-driving labs on different applications to illustrate, oh, it can work. And also we are building some protocols and we are building some standards for the community to group together. But what would be the like the top challenges or the top problem we should solve first toward that direction, the AI scientist?
Yeah, it's an interesting question.
Sorry, it's a little bit
Yeah.
philosophical, I know.
So, well, I don't know if it's the top, but one I'll talk to is really teaming. And so, you know, if you work in a research group, you're part of a team, and that teaming is critical to how well you do, and that's true in lots of things, not just research. And how do we then build ways of teaming, human machine teaming, with research, robots, self-driving labs? And you know, there are people who study that for a living, right? And if you think about, you know, you get into, well, for me, it's with my phone, right? I'm constantly frustrated with Siri about how Siri doesn't understand what I mean. And Siri's probably frustrated with me because, I'm not getting it either, right? So how do we communicate properly? And how do we have better division of labor? And so there's a slide. I'm not sure if I have this slide. Hang on.
Yeah, this is really great and a different angle to me. It's quite innovative because what I have been thinking about is like to have autonomous or automated analysis pipeline would be the top priority because now we can clearly use these robotic arms to move stuff. We have self-driving labs, but how can we analyze the tremendous data coming from these machines in an effective way, in a less biased manner? So that's what I have been thinking about. But yeah, as you mentioned, like the teaming, the community are all important stuff.
Right. And so teaming there, so the example is from CAP is this human robot teaming for chess. So, chess playing robots, really software, have been better than humans by themselves for a long time
Yeah.
now. But what
Yes.
surprised me is that humans plus robots are better than any chess playing software by itself. So humans plus robots beat humans, but also beat computers.
So,
Go ahead.
oh yeah. So is it like a way to incorporate our human expertise in the algorithm, like physics informed models or
Yep,
heuristic inspired models? Like
that's right. All of
I
those.
see.
So how do we incorporate, how do we represent? Representation is a big
Hmm.
problem, but how do we represent the human knowledge? How do we solicit or elicit human knowledge? So we have a paper where we did uh, human preference on what was a good looking vase, what was an attractive vase shape. And so there, the human couldn't put into words or mathematical definition what made a good looking vase, but just through an A/B analysis, essentially the human was presented, and we published this last year. The human was presented with two images and asked to pick the one that they liked better. And then by doing that iteratively over a series of
Hmm.
experiments, the system learned the human preference for what was a good looking vase, right? So there's ways to
I
do that.
see.
But the one on this one is just that the tagline is that not only did the human computer team beat everybody else, right? But the winner was not the grandmaster chess players plus the supercomputer. The winner was good amateur chess players with 3 desktop computers who had superior teaming. Okay. And it was the superior teaming that made them the winning team.
I see. Yeah, that's quite interesting. So speaking of like the human in the loop you mentioned, what effective strategy do you think we can use to reduce the subjective opinion or like to ensure the conclusion is not heavily biased?
Yeah, that's super important. And I think that requires a lot of uh, oversight and vigilance. And I think there's already a lot of bias in foundational models. And so we first have to sort of repeatedly ask ourselves that question, how might we be biased? And that's part of good science anyhow, but in this situation where we start delegating decision authority, we sometimes forget about that. And so, there's a an early example, it's not published, where we shared some results with on Aries with some collaborators who did a machine learning analysis, a statistical analysis of our results. And we gave them all the data, including the pillar coordinates. And they said, oh, well, look, our result shows that the pillars that are along the edge of the sample had different behavior. We're like, that's not supposed to happen. Well, it turned out that our catalyst deposition changed towards the edges of the sample. But had we not included the pillar locations, they wouldn't have known why that was true, right? And so,
Yeah.
so if we had been biased and said, oh, well, we had said, well, all the pillars are the same by decree, that we would have lost that insight.
I see. Yeah, that absolutely makes sense. Probably like more peer review mechanism on this stuff. Yeah, and thank you so much. That helps a lot. So yeah, I think we're right on time. And before we wrap up, I want once again to express my sincere appreciation for you for bringing these amazing, these innovative and transformative research with us. So thank you, Benji. Yeah.
Thank you. Thanks everybody for your attention. And yep, hopefully look forward to talking some more.
Perfect. Yeah. Have a great day, guys.
Thanks. Bye-bye.
Bye.